Hello. Is that working? Hello. Okay. I guess hopefully people at the end can hear me. Okay. And okay. And so hopefully, do people have questions from last time? If not, then yeah, let's continue our chapter 1. And I think we should go faster today because yeah, we are in quite tight schedule at the first half of our semester. And here is a small review. So we have reduced row ratio form. This is when we solve linear system on augmented matrix. This is a form matrix that we want to make our augmented matrix into. So it's a whole bunch of these ratio echelons. So you will be reduced to this upper triangle matrix. Upper triangle matrix, and with the leading element of each row being 1, and everything above the 1 being zeros. This is the reduced row echelon form, and you can use the three elementary row operations to make any matrix into a reduced row echelon form. And that process is called Gauss-Jordan reduction. Okay, and quick review is like this. So you pick rows one by one, and you look at this PV row and make everything under the PV0 by adding or subtracting the PV row to other rows. Okay, and so you can get this upper triangle. Then you go from back and you look at the PV from each row and make everything above it into 0. Then in the end you will get this. In the middle, you also want to multiply by some number to make your leading rows leading element 1, and then you will get this reduced row echelon form. Okay. And so here is a slide for steps of the Gauss-Jordan reduction. So in the first step, we make the I guess this is not strict triangular. Okay. In the first steps, you make the matrix triangular, so not strict. Okay. And excuse me, where am I? Okay, close out. Okay. First steps, you make the matrix strict triangular. Then you multiply some number to make the leading number of each non-zero row 1. You become the row echelon form, and you subtract from the less row to upper rows to make the reduced row echelon form. Okay. That's a quick review of last time. Then we have a homogeneous system. So system is called homogeneous if the right hand side are all 0. So homogeneous system is I guess it's a system of linear equation, and you think about its augmenting matrix. If everything to the right of this straight line is 0, then that system is called a homogeneous system. And homogeneous system is nice because it's always consistent, because you can just put OX being 0, then it will be a solution to this system, because the right hand side of the equation are all 0, so if you put the OX equal to 0, then it will be a consistent solution. And we like homogeneous system because In later part of the course, you will see that you can use a homogeneous system to analyze systems that has many solutions. Okay. And here we have a small theorem about homogeneous system with underdetermined system. So if you have a system that's both homogeneous and underdetermined, then you must have a solution that's non-trivial. We call it a non-trivial solution. It just means a solution that's all zero. Remember, homogeneous system always has this trivial solution being all zero. And if it's also underdetermined, then it must have a solution that's not that all zero solution. Okay, and the proof is quite simple. So a homogeneous system is always consistent. And remember, we also say that the underdetermined system either have no solution or has infinitely many solutions. It cannot have just one solution. Okay? And so this system must have more. Yeah, it has a solution, and then it must have more than this trivial solution. Okay, so it has a non-trivial solution. Okay, and that finished our 1.2. So there are some checkpoints for 1.2, and so in 1.2 we learn how to find the solution of a system. Okay? And you will also see whether it's since we found a solution, you can see whether it has a unique solution, infinite solution, or inconsistent. And to do so, we find the reduced Roche form and using Gauss-Jordan reduction. Okay? And also there are overdetermined system and underdetermined system. Overdetermined system means there are more equations than unknowns, and underdetermined system means there are more unknowns than equations. Then there are rotational form and the reduced rotational form, and there are homogeneous system. Okay, and then we go to next section. That's 1.3, and it's about matrix arithmetic. So we are going to talk about addition and multiplication of matrices. Okay? And this should also be a review of your high school math. Okay? And first we have some notations. So a matrix is a block of numbers. So n by n matrix is this block of numbers with height being n and width being n. Okay? So there are n times n numbers inside. And each entry are called a scalar, or we call it a matrix element. And those scalar is just a number. Each scalar is just a number. It's a real or complex number, but in general, in this course, it should be a real number. And we'll use this notation. Aij means is sorry, I have this wrong. Aij will be the ijth element of this matrix, and have ij swapped. Sorry, so this should be I, and this should be j. Okay. So it's an element on ith row and jth column. Okay, just aij, and there are more notations here. So this whole matrix will represent it as this curly bracket and small aij. Okay. So curly bracket small aij is shorthand for this whole matrix. This whole matrix with m times mn element. And also there are more notation for this matrix element aij. Okay. So if the big matrix is big A, and I guess the most standard notation we have for element is small aij, but we will just sometimes just write big aij because it's the ijth element of this big matrix big A. And or we have this bracket A and ij. Okay. So yeah, I think the book notation is small aij, but sometimes we use different notations. And also a bit of a side note, in MATLAB, the mathematical program, if you want to assess the element of your matrix, is written as big A and parentheses I comma j. And yeah, some book will also use this notation. Okay. So this is a matrix notation, and we also have a vector notation. And vectors simply are just now is just a smaller matrix. Okay. So vector is just n numbers putting together in some sequence, in some order. And so there are row vector and the column vector. So we basically think vectors are special cases of matrices. So row vector is just a matrix with only one row. And then here the important thing is we have two notation. I guess let's finish this first. So row vector is a matrix with one row. So like this is a matrix with say n element. So a1 n2 to an. And column vector is a matrix with one column, and it's like this a1 to an. And notation that we'll try to keep consistent throughout this course is notation for row vector and the column vector. So row vector will be written as a small case small case letter and with arrow on top and also boldface. And the column vector will be written out like this. So will be boldface small case letter. Okay. So column vector, row vector, and also we have this another notation here. This Euclidean n-dimensional space is the set of all n by 1 matrices. So the set of column vectors that has a real number inside and with length being n is called the Euclidean n-dimensional space, and it has this notation Rn. Okay. And so we can use this column and the row vector notation back to represent a matrix. So a matrix as a block of numbers, it can be written as a collection of even columns or rows. So here we use the column vector notation to represent our matrix. So we think our matrix A this block is a collection of these columns. So A1 will be the first column here, and A2 will be the second column here, etc., and all the way to the AN. Okay, so A1 will be this column vector, A2 will be this column vector, AN be this column vector. And we can also think A as a collection of row vectors. So we'll have this A1 row being this first row here, A2 row being the second row here, and AM row being this mth row here. So this is some notation that you should keep familiar with because we'll use them quite a bit later on. Okay, so column vectors and row vectors. And just need to memorize the rotation where row vectors are the vectors with arrow on top. Okay. Okay. And and here is more detail about the notation we just have. So we have the row vectors. So row vectors in terms of matrix A, if you write down the element explicitly, it will be rows element. So it's row ith row. So it's rows element with I as the first index, and the column vector is the jth column vector is vectors on jth column. So you have j as the second index, etc. And let's see these are some examples. So A is 325 and 184. So the first column vector will be this 3 minus 1, and here we have the second column vector, and here we have the third column vector, and then we have the first row vector, this thing, and the second row vector. Okay. This should be quite intuitive, just a notation for column vector and the row vector. And then we have equality of two matrices, and two matrices are equivalent. Equal if only if all elements are equal. So all small ij are equal, and also this means their dimension needs to be equal. And then next we have scalar multiplication. So scalar multiplication of matrix is written in this way. So we have a matrix multiplied by a scalar. In terms of algebraic expression is alpha A, and this gives us another matrix that has the same dimension with A, and every entry is alpha Aij. So every entry of the matrix gets multiplied by this alpha. And here we have some example. A equals this thing, and we have 1/2 times A. Then all the entries got multiplied by 1/2, and we have 3 times A, and all entries got multiplied by 3. Then we have a matrix addition. It's also quite intuitive. So we have two matrices with the same size. Then we can add them together, and we just add every entry together. So we have those two matrices add together. Let's say we have 3 plus 2 become 5, and here we have 5 plus 2 become 7, etc. And here we have also have 2 entries. So this 218 plus minus 8, 3, 2, and every entry get together. So 2 plus minus 8 become minus 6, etc. Okay, this is matrix addition. Okay. And then we have a BMO notation of matrix addition. So we also have a matrix subtraction. Just means we're adding the minus 1 times the second matrix. So A minus B just equal to A plus minus 1 times B. And we can also have, so this is not standard notation, so we can also think about the all zero matrix. So if we have a matrix that's all entries are 0, then will be the additive identity of the matrix addition, means that everything addition to the 0 matrix will become the same matrix, and you can add from left and add from right and add from left will be the same matrix. And also every matrix has an additive inverse, means that you just add a minus 1 of yourself, then it becomes the 0 matrix. Okay, and then you can just denote that matrix as a minus A. This should be quite simple. Then we go to the more complicated part of the algebra, but it should still be your high school. This is matrix multiplication. And here we have intuitive definition of matrix multiplication. So you can multiply 2 matrices together. It's only possible if the matrix has 15 dimensions. Means that the number of columns on A and the number of rows on B must be the same. And that's the case because how you calculate the multiplication of 2 matrices A, B. So if you have n times r dimension A, dimensional matrix A, and r times n dimensional matrix B, then the resulting matrix AB will dimension n times m. Okay. So the number of number of rows of A and the number of columns of B. So n times m. And then we define this AB entry-wise. So the ijth element of AB will be the ith row and the jth column of AB multiplying together. And by multiplying together, we mean we do this. We sum over all the multiplication of each element one by one. So the ikth element, so we sum over this k. I guess I should mark this sum over k. So k from 1 to r means that k going from this 1, 2, 3 to r, and this 1, 2, 3 to r, and we multiply each element from A and each element from B together, and we add together those multiplications. Okay. And yeah, that's a matrix multiplication. And here we have more mathematical definition. If matrix A has elements Aij and matrix B has the element Bij, and we multiply together become matrix C with elements Cij, then Cij will be this Ai row vector multiplied with this Bj column vector, which means summation over k and Aik times Bkj. And I guess see some example. So for example, we have this AB being 3 by 2 matrix and 2 by 3 matrix, and we can multiply AB together. Then for example, we have this 2, 3 element. It will be 2 times 3 plus 4 times 6. And we need to do this multiplication, addition on every element, and we'll get this we'll get this matrix AB, and we call this C. Then C23 will be this element, which is 30, because it's equal to 2 times 3 plus 4 times 6. and we see that C is a 3 by 3 matrix. And the interesting thing here is that in this example, because the dimension happen to be fit, we can also have a matrix BA. And the matrix BA will be a different matrix from matrix AB because they have a different dimension. Now matrix BA will actually be a matrix with dimension 2 times 2. And you can write it out, will be this, calculate it out, will be this 2 times 2 matrix. So you see that in general, AB and BA are different matrices, and sometimes BA might not even exist when AB exists. Okay. And I guess here is the example where BA exists and AB don't exist. Okay. And so we have a matrix B and the matrix A. We can calculate the matrix BA being this 3 by 2 matrix. But if you try to write our matrix AB, then you see that the dimension doesn't fit, because the second dimension of matrix A is 2, and the first dimension of matrix B is 3, and the 2 don't equal to 3, so matrix AB don't exist. And so this is where matrix multiplication is different from scalar multiplication. In scalar multiplication, you always have this commutative rule, where say 3 by 5 equal to 3 times 5 equal to 5 times 3. But in matrix multiplication, if you change the order of multiplication, the multiplication might not even exist. Okay? So commutativity, matrix multiplication, is not commutative in general. Okay? And if you have A and B both being n by n matrix, then A and B have A. AB times BA are both same dimension, but in general they still are not equal. Okay, matrix multiplication is not commutative. And here is an example of a square matrix being not commutative. So you have A and B, and AB equal to this 3, 3, 1, 0, 0, and BA equal to 1, 1, 2, 2. And so you see that AB don't equal to BA. Okay. And again, the small application of multiple multiplication or a multiplication for defining matrix multiplication in the form we have is that we can use multiple multiplication to write the linear system. So I guess this is really a repetition of what we talk about linear system, but just changing to a different notation. And remember, those linear system equations is equations with a whole bunch of coefficients and axes, and then go to augmenting. I guess that's right down somewhere. Okay, so linear systems are like those x1 plus x2 equal to 1, and maybe x1 minus x2 equal to 0. And so abstract to augmenting matrix, we say we don't want to write those axes, and we just write this augmenting matrix like 1, 1, 1, and 1 minus 0. And then here we kind of been doing a little dumb thing. Then we say, but we kind of want to this axis back, so then we use the matrix multiplication rule to write this equation instead. So we have write this in terms of ax equal to b, and with a equal to 1, 1, 1 minus 1, x equal to x1, x2, and b equal to this 1, 0. Okay, and now we don't need to write x so many times, and but we still know our x are x1 and x2. So this is basically what we do here. And let's see this work out in some smaller case. So say our equation is just only one equation. We have this 3x1 plus 2x2 plus 5x3 equal to 4. And our A is this matrix with one row, and X is this vector with x1, x2, x3, and B is this 4. And we can have Ax equal to B as this. And we check out this Ax equal to 4, x3 equal to this equation. Because we have A like this, X like this, then Ax will be 3 times x1 plus 2 times x2 and 5 times x3 by our matrix multiplication rule. So it is 3x1 plus 2x2 plus 5x3. And that's exactly this left-hand side of our equation. Okay, and we can generalize this a little bit to symbols. So a with this a1 to an, x being this x1 to xn. Then you see this ax equal to this ax1 plus a1x1 plus a2x2 to anxn. And system can be written as ax equal to b for one equation. And here we do a bit of digression. So from this, we also see one of the definition. That's a scalar product. Okay. So scalar product is something we already seen before. It's matrix multiplication of row vector with column vector. And we see that this always gives us a scalar. And we already see this when we define matrix multiplication. So remember, we have this thing. We say each element of the multiplied matrix is this row times this column. Okay? And we see that this row times column actually also satisfy the matrix multiplication rule. And this row vector times column vector is called a scalar product, and give us a number, which is this ijth element here. Okay, so that's a matrix. That's a scalar product. Okay. Just a row vector and a column vector with same dimension multiplying together, then it becomes scalar, and that's called a scalar product. And sometimes it is also called the inner product. Okay, it will be an important concept later when we talk about inner product space. And anyway, let's back to writing a linear system with ax equal to b. So now we have four linear system with this m equation and n numbers, and we can still write this as ax equal to b, with a just equal to the coefficients on the left hand side, and x is these vectors of unknowns, so x1 to xn, and b being the numbers on the right hand side. And then you can try to do the matrix multiplication out. Then you see the first element of ax will be this first row times these columns, so will be this a11x1 plus a12x2, etc. So will be the left hand side of first equation and equal to b1. And similarly, the second equation will be this row times this column, etc. And we see that a is equal to b. This column vector equal to this column vector will exactly reproduce our linear system equation. Okay. And here are more notations. So the ith entry of ax will be the ith equation, okay, being the ith row of a times this column vector of x. Okay, and we can write ax as this vector of each row times this column vector of x. And here are some examples of ax. So first row times the column, this column of x becomes this equation. The second row times this column becomes this equation. And here are some more ax equal to this thing. And here are some ax with x being some number, then you see it becomes some number. Okay, and yeah, so more example. Here we have a linear system equation example. We have a 3x3 linear equation here, and these 3x3 coefficients become this A matrix, and we have x vector here, etc. Okay, and here we have another concept that will be useful. Is just we think about. I guess it's now it's out of solving linear system. We are thinking about what happens when a matrix time is multiplied by a column vector. So we think about the product X, and we have this is a matrix times a column vector, and it will become a column vector as we know. But here, the important thing here is a different interpretation. So you can think about this as a sum of column vectors, because when we write it out, it's this it's this summation of a linear equation here, and we see that it's this column vector times x1 Okay, so let's do this step by step. So we write down AX is this column vector, where each entry is this summation. So A1x1, A11x1 plus A12x2 plus all the way to A1xn. So we can think about this as the sum of those column vectors. Those column vector with A11x1, A21x1, all the way to AN1x1, etc. So these column vectors with x1 and those column vector with x2. And this column vector all the way to this column vector with xn. And then we can think of this column vector because every entry here is multiplied by x1. So it's x1 times this column vector plus x2 times this column vector all the way to xn times this column vector. Okay. And those column vectors are just the column vectors of A, and it's written as this, remember our notation is this A1 column vector of A, and the A2 column vector of A, and all the way to AN column vector of A. So you see that this AX can be written as this linear sum of column vector of A, where the scalar coefficient here are x1 to xn. Okay. And yeah, so this is a nice thing to remember, where matrix times a column vector can be think of as a linear combination of the columns of the matrix. Okay. So and remember, those AI are column vectors of A. And here is an example. So with A and B written as numbers, so this equation can be written as this 2 by column multiplied by x1 and 3 minus 4 multiplied by x2, etc. And here we have the concept of a linear combination, which will also be important later on. So linear combination is just a sum of a whole bunch of vectors, where each vector is multiplied by some scalar. So we have some vectors a1 to an, and multiply with some vectors c1 to cn, and adding them together is called a linear combination. And so we see that the AX can be thought as a linear combination of the column vectors. Okay, and yeah, so more example, we see that if you put x as some number, then this AX part is a linear combination of the column vectors, etc. Okay, so we have a linear combination of columns. And then we can generalize this idea a little bit. So when we see matrix multiplication, so n by k matrix times k by n matrix, then this n by n matrix, we can think each column of it as a linear combination of the columns of the first matrix, because the first column will be this matrix A multiplied by the first column of B. And if you just fit the geometry here, and then the second column of AB will be the matrix A multiplied by the second column of B, etc. And all the way to the next column of AB will be the matrix A multiplied by the next column of AB. And in terms of algebraic expression is this. So each column of AB will be this A times column of B, A times column of A times first column of B, A times second column of B, etc. Okay, and yeah, and the ijth entry can be single of the ith entry of the jth column here, which is A times Bj. Okay, so here are something about Ax equal to B. Then lastly, you have more definition. So we define transpose of a matrix. So every matrix we can define a transpose. So a matrix of dimension m times n, or its transpose will be matrix of dimension n times m, and where the entry just have the swapped index. So bji will be equal to aij. Okay. And yeah, and it's denoted as is a to the t. Okay. And basically we swap the row and the column of this matrix. So you have this H matrix being 1, 2, 3, 4, 5, 6. They will become this matrix with rows being 1, 2, 3, and 4, 5, 6. Then A transpose will be this matrix with columns 1, 2, 3, and 4, 5, 6. And similarly, we have, and you see that this is a 2 by 3 matrix, and you do transpose, it becomes a 3 by 2 matrix. And yeah, similarly, you have this 3 by 3 matrix, and you can transpose to this 3 by 3 matrix. And yeah, and you see that another way to see this, you swap the off diagonal elements. And so you see this 4 swapped by 2 with 2, and so you see 4 swapped by 2. Okay, and sometimes the matrix will be same as its transpose. So we have the C matrix with same as its transpose. Okay, and yeah, and when that happens, we call the matrix symmetric. And it want to be a symmetric, it must be a square matrix. It's an n by n matrix. And yeah, it is symmetric if only if A transpose equal to A. So you see that you need to have the off diagonal element being the same, that is Aij being equal to Hij. So it has this symmetry. So this 3 equal to 3, 4 equal to 4, and 5 equal to 5, etc. Okay, so that's transpose and a symmetric matrix. And here is a quick checklist of 1.3. So we talk about matrix operations. So there are a whole bunch of matrix operations. And so basically there are scalar multiplication, addition, and matrix multiplication. And matrix multiplication being the most complicated. And there are also other concepts like equality, additive identity, and additive inverse. And important to note, matrix multiplication is not cumulative. Then we talk about using matrix multiplication to describe linear system. Once again, we can describe linear system as A is equal to B, where A is a matrix, X is a column vector of matrices, and of unknowns, and B is a column vector of the right-hand side of equation. Then there are scalar product of a matrix is row vector times column vector, and there are linear combination of vectors, and there are transpose and a symmetric matrix. Okay. Okay. I guess we should have one more note here, and we need to remember matrix notations. And so like Aij and A. I guess the thing I do more is there are Aij, and sometimes also write Aij, and also row vectors. This okay, it's hard to do bold case with a pen. Okay, this is bold case A, and there are row vectors and also the column vectors. This is bold case A. Okay, it's also important to remember the notation. People have a question? If not, then let's go to next chapter. I guess next PowerPoint. And let's go to 1.4. Too long. PPTX. And this. Let's see if this work out. And oh, it should work out. Nice. Okay, and yeah, let's go to 1.4, and we have even more matrix algebra. And here are some matrix algebra rules about multiplication, addition, and matrix, and well, addition and matrix multiplication and scalar multiplication. And I guess they are mostly the rules that are expected to happen for addition and multiplication. The most important rule is something that we don't have a rule, is AB don't equal to BA in general. And but I guess a bit special, a bit more surprising one is AB don't equal BA, but you have AB times C will be equal to A times BC. Okay? And we don't prove all of them, but we'll try to do a bit of it. Okay? And so you see that you have those associative rules and distributive rule, etc. Okay? And I guess this one is a bit special, and these two are a bit special. The distributive rule for matrix multiplication. Okay? And yeah. So here is some examples. So we have ABC, and you can do the multiplication to check out. So you have A here, and you multiply BC together, then you multiply with A. You see this matrix. And if you multiply AB together first, and then you multiply BC, you see it's this matrix. Okay. And yeah, so A times BC equal to AB times C with this special example. And you can also check out the distributive rule works out. A times B plus C will equal to AB plus A times AB plus AC. Yeah. And here we have a bit of proof. I guess the proof is here to make you familiar with this algebraic expression to do proof. Okay, so let's say we have ABC, and now we see the notation is a bit annoying because now we need to have a symbol for each matrix to write down its element. But anyway, so A equal to Aij, A with element Aij, B with element Bij, and C with element Cij. Then we also write have a name for this matrix, which is A times BC, B plus C, and the matrix is AB plus AC. And let's just go by rule and see what are the elements of Dij and the element of Eij. Okay. And so first we have elements for B plus C will be is Kj's element will be Bkj plus Ckj. And then we have Ij's element of D will be the Ik's element of A plus multiply with the Kj's element of B plus C, and adding the K together. So that's Ij's element of D. And similarly, we have the Ij's element of E will be Ij's element of this AB plus the Ij's element of this AC. And it will be similarly have a whole bunch of sum K. So sum K and Ik of A and Kj of B. And similarly, we have Ik of A for this A and Kj of C from this C. Okay, so we have Ij's element of D like this, and Jk's element of E like this. And now we just want to check this equal to this for every Ij. And this can be now done by just the distributive rule of scalar addition. So this thing, each element is this AB plus AC, and summation of two things, you can just write down different summation. So we see that for every Ij, Dij equal to Eij, so these things are equal. Okay. And then we can do a bit of harder rule. So we can check this associative rule of AB times C equal to A times BC. And once again, we have a name for this A times B and a name for this B times C. And then we have the IL's element of this thing will be AIK plus times BKL summing together. And because it's A and B. And the Kj's element of this thing will be BKL times CLJ summing over L. Okay. And then now we can think about Ij's element of DC, which is equal to this A times B multiplied by C. And so we sum over L from 1 to R of this DIL and CLJ. And this will be a double summation. Now we write down this DIL as this summation. Okay, so it's the sum over KC and AIK, BKL, and CLJ. And then also the we have different notation. Ij is entry of AE, which is this expression, is similarly some AIK, EKJ, and we substitute this E inside, so we now also have this sum over L. Okay. And now we want to see this thing equal to this thing for every Ij. Okay. And we change this thing equal to this thing. Okay. So we have the summation L, summation K, and what we do is we can pull the C inside the summation, and then we can change the order of summation and pull AIK out, because we see AIK has nothing to do with this summation of R. Yeah. And then we get this expression. Okay, and then we compare back. We see this expression same as this expression. So we know that AB times C equal to A times BC. Okay. Yeah. So anyway, here is hopefully this day you learn how to write some proof for matrix properties. You just write down the element in terms of algebraic expression and a whole bunch of summation, and be careful about the index you are summing over, etc. Okay. And yeah, here is some hard proof, and let's go to more notation. And we have notation for powers of matrix, and it's only for n by n matrix. And when k is some positive integer, then we can always define it to a k. It's just a multiplied with itself k times. Okay, this is quite intuitive. So say a equal to this 1111, then a squared is just a multiplied itself will become this 2222, and we can have a cube, which will equal to a times a times a equal to a times a squared. And you will equal to this 4444, because this element is 1 times 2 plus 1 times 2 equal to 4. And you can easily see that a to the nth power will be 2 to the minus 1. Okay. And then we have more notation. So this identity matrix, and this is kind of bad notation, as we will see very soon. So identity matrix I is when we write I is identity matrix, but it actually means a lot of matrix. Okay, and so they are actually an identity matrix for every dimension. Okay, okay, and so if A is a n by n matrix, then there we multiply left on its right by this matrix. Identity matrix In, then you will go back to the matrix A, and then we can multiply on its left with this identity matrix In, then we'll also get back to this matrix A. Oh, sorry, I write this wrong. Okay, and this In and Im are different matrix, because In is a matrix of dimension n by n, and the matrix Im is a matrix of dimension n by n. Okay, so there are matrices with different dimension, but often we just abbreviate the identity matrix of all dimension as I. So it's a bit of confusing. This will be written as A times I. This will also be written as I times A. And but this I and this I are different matrix, because you can just see they must have different dimension to be able to be multiplied by on A. Okay, and yeah, so identity matrix of size n is this n by n matrix I, and it has an element being delta ij, and delta ij is this delta symbol, where we'll also use a lot later. I guess it is called a delta function. And delta ij is this function where it equal to 1 if I equal to j, and 0 if I not equal to j. And if you write down this as a matrix, it's just a matrix where the diagonals where I equal to j are 1s and it's a 0 all where. And here we can see some example. We have a 3 by 3 identity matrix. It is a matrix where diagonals are 1 and 0 all where. And you can see that you multiply this on matrix A on the left, and it becomes the same matrix. And let's check a little bit. So let's say the first element here, you will be this 1 0 0 times this 3 2 0, and it will be this 3. And say this element 4, you will be this 1 0 0 times 4 6 1. So it's 1 times 4 equal to 4, okay, etc. And similarly, you multiply identity matrix on the right of a matrix, you also get back to the same matrix. Okay, so those are identity matrix. And you can check where A is not a square matrix, you will also see the same result. And from identity matrix, we also snug in more notation. We have standard vectors. And standard vectors are vectors. Here we have a funny definition. It's a vector that are the column vectors of an identity matrix. Okay, so column vectors of n by n identity matrix are the standard vectors in the Euclidean n-dimensional space. Okay, and you have this notation with EJ. Remember, bold-faced number is a column vector. Okay, and so we say column the column vectors of identity matrix somehow it's not a small I, it's a small e. It's E1 to En. Okay. And if you write down the vector, you will have this form. So EJ will be this column vector where it's 0 all other where with 1 on the jth column, okay, and also on the jth row. And for example, so we have E1 equal to 1 0 0 here, and E2 for 3 dimension equal to 0 1 2, and E3 equal to this 0 0 1. Okay, so those are standard vectors. And yeah, we'll always express standard vector with this EI, EJ. Okay. And okay, I think it's a good time to stop now because now we can take a 10-minute break. Yeah.
就是想问那个，最近还有多少名额？
其实名额基本上没有了，我不知道。我看是还可以加，系统上还有一些名额啊，但是我是尽量不太想签，因为我们已经蛮多人了。现在到底我问一下好了，所以另一个班也签不了吗？
他赢全满，然后我现在在等重复修读的那个
重复修读，所以我们是有一些名额啊，但是就是可能要比较好留。好，我看一下，这里可以看到人数吗？因为我就觉得，我以为我已经签到140，但是有同学退掉吗？看一下，可能你这边现在的人数，我可能看一下系统，等一下。我这边可以看到人数，像123。哦，那我们可能可以再签一些这样子。现在140 ，OK， 所以重复修读可能可以吧
？OK， 那我等他们下来再签。
好，
谢谢教授。
OK， 然后其他同学是，好吧，那我们来看一下其他同学。对，那我你有，让我想想，你有寄信给我吗？我有点忘记我是怎么，
我没有，
我上次有记录你吗？
有，上次是我直接过来这边。哦，
然后我要记得你是哪一位同学吗？
有，我记得怎么有记，
我记得
130622335。
哦 ，OK。让我想一下，我记在哪里？
我记得好像是记在电脑吧。
电脑。等一下。好吧，那先这样子。好，我再找一下。好，那这样重复修读，然后其他同学是
这门课的简报。
简报是什么？哦，
因为没有在那个系统里面。
系统里面的话就有简报这样子。OK。 可能要有系统。所以同学你是还没有加签吗？还是？
没有加签，没有加签。
哦 ，OK。
清华学院学习。
清华学院的同学，清华学院我加签比较少。我看一下。所以同学们，好吧，那我们一个一个来，可能主要还是线上系统吧。但是如果是120几个人，我们这个再加签一点这样子。可能我还是线上系统考虑。但是通常我不知道你们是几年级，1年级的同学我就不加签了，因为这2年级的课这样子。对，所以我不知道同学都是什么状况。啊，那可能同学可以一个一个陈述一下你们的状况。
上礼拜有送那个线上加签，但是那是不合格。
对，你是？
我想问一下，是为什么？
你是哪一位同学？我看一下，
工学院是失败。
同学哦。
第二专场是。
因为电机，我想说电机应该要去签电机系的线性代数。
因为时间冲堂的关系，没有办法。
因为我是因为有电机系的线性代数，所以我是以可能是资工系列的专长为主这样。那有名额的话，我可能会考虑再加签一下这样子，对吧？那你们可能就在中间这样，对吧？所以我先退，有些我先退掉，因为是电机系的专长。我想说电机系会以电机系的课为主这样子，对。
如果要这门课上课简报的话，
可能要等，可能跟同学要一下，或是等到签章再有这样。
就是在问，期中或者考试会有这个题。
可能会有啊，maybe 都给人听。
我是理学院学士班大三。
对啊，然后是。
那我
也是二专，也是电机的，是不是？
哦，对。
那可能你们就再申请一次吧，有些名额，那我看名额够的话，我再开放这样。对。因为电机业我是第一时间退掉了，就是因为你们电机也可以修电机系的课这样子。对。
我是清华学院的，然后虽然就是休学，因为我是有休学到1个学期，所以虽然我现在是显示是1下，可是我这学期应该要修2上的课，不然我后面不然我会差1个学期。
好，清华学院，所以你也是想要转资工系嘛？好吧，那就请你们再送一次这样子，再送一次申请。
我是辅系的，然后
辅系的话，
他说我那个是就毕业必须然后资工系办也是说只能修就是资工系。
是辅系这样的话，好，如果辅系只能修资工系的课的话，那我就帮你签下了。OK， 好，谢谢。
老师，我再重送。
那你再重送一次，对。
清华学院蛮大的，但是我在别校修课，就是一些资工的课程，大一的都低免掉。
那
就我现在要修大2的，我又没有办法签，然后就是去修一些别的课。
那我觉得你的问题比较不严重，所以我们再考虑一下，因为你可以明天再修，对吧？你这个是进度比较超前这样子，对吧？那的确 OK， 比较优秀的同学。
最近要加钱的样子。
听起来应该是这一些人吧，就是有在跑来的人，可能剩下5、6位嘛，应该还是130的话，130我们还可以回，对的。可以，应该可以。顺便问你，我们有什么时候可以瞧你过来办公室做人家的那个 UPS？ 今天吗？
老师
下午我不知道什么时候要跑掉，其实下午应该是有空的，对啊。
下午3点10分的时候。
那可以啊，3点10分，好，我们装一下。OK， 感谢。 Okay, let's go back to linear algebra. Let's do more math. Okay, so guys, we say we have a lot of notation, and it's a bit important to remember what's identity matrix and what those are standard vectors. Okay, so these are easy concepts, but just need to remember the notation. Otherwise, sometimes we might just write the EJ, and then you don't remember what's EJ, then it will be very confusing. Okay, and also identity matrix is also an easy concept, but you just need to remember the notation I or I sub n. Okay, and back to matrix properties. So we have a whole bunch of matrix property, matrix algebraic rule here, and now we have the something we avoid for quite some time about matrix algebra. That's the inversion of matrix multiplication. So there are matrix inversion. Okay? And here we start with a bit of a multiplication. So remember, when we have a multiplication of real number, is most of the time we have inverse. So that's we have some number a, then we can find some number b where a times b equal to 1. Okay? And so every number that's not 0, you can find the b as 1 divided by a. Okay? And we want to find a similar thing for matrix inversion. And here, I guess the big important thing is this only works for one n by n matrix. Okay, so for any n by n matrix, we can try to find its inverse. Okay, and inverse matrix is a matrix B such that AB equal to BA equal to the identity matrix I. Okay, and B is called multiplicative inverse. Okay. And but the matrix inverse don't always exist, just like number inverse don't always exist because 0 don't have an inverse. This is standard thing, so you know that 1 divided by 0 is don't exist. Okay? And similarly, there are many matrices that has 0 somewhere that don't have inverse. Okay? But when a matrix has inverse, it's called non-singular or invertible. Those are just names, means you have an inverse. And also we have a definition here where we also smuggle in a bit of a theorem. And so remember, we have before we say AB don't always equal to BA. Okay? But here we see that in this definition we kind of see that AB always equal to BA. If B is a matrix inverse. And this is actually a theorem that is not so easy to prove. You need to spend some effort to prove it. And the theorem is that if AB equal to identity, then BA also equal to identity for square matrix AB. Okay. And anyway, with some sparkly in this theorem, then we have matrix inverse is matrix B such that AB equal to identity and BA equal to identity. Okay, and yeah, then we have a bit of a theorem here where we want to prove that the matrix inverse are always unique. So there is at most one matrix inverse for a matrix, and say we have two inverse of the A. So we have AB equal to BA equal to AB equal to BA equal to identity, and CA equal to AC equal to identity. Then we can think B as B times identity, and we have identity equal to A times C, and then we use the associative rule of matrix. Then this is equal to AB times B times A with C. Then we know B times A equal to identity, and identity times C just C. And here we see we have quite a clean proof that B equal to C, where we don't need to write down the explicit matrix element. We just have this algebraic expression, and we see that B equal to C because we have all those matrix. We have those multiplicative inverse rules. Okay. And here I have a notation. So the inverse of a matrix is denoted by a to the -1 power. I think this should be pretty intuitive notation. Okay, and here we have some examples. So if you have 2, 4, 3, 1, and this -1/10, 2/5, 3/10, -1/5 will be its matrix inverse. And we can multiply both from right and from left to see its identity. Let's check some element. Maybe this one element will be 2 multiplied by -10, and 4 multiplied by 3/10, and adding together. And so it's 1/10 times -2 plus plus 4 times 3. So it's -2 plus 12 equal to 10. So this is and over 10 it becomes 1. And similarly, let's say maybe this 0, and it's 3 times -1/10 times 1 plus 1 times 3/10. So it's 1/10 times -3 plus 3, and it's 0. Okay, and you can check similarly. It's with the left multiplication, it's also giving you the identity matrix. Excuse me. And we have more example. You can try all the matrix multiplication yourself. And this matrix has this matrix as its inverse, and you multiply by right, multiply by left, is all giving you the identity matrix. And then we have some example of matrix that has no inverse, and it's this matrix A equal to 1, 0, 0, 0. And here you can intuitively think you don't have an inverse because you have this 0 here, and 0 don't have an inverse. And if you have more proof, so suppose we have some inverse B with those elements B11, B21, B12, and B22. And say you multiply B on A on the left, and so this B with A, and we write down all the elements. And so first column will be because you multiply with this thing, and the second column will be 0 because the second column of A is 0. And you see that this element is 0 here, and it can never be 1. And but for identity matrix, this 2 element must be 1. So the 0 here means that no matter how you pick B, B times A will not be identity matrix. Okay, and we have a name for matrix that's not invertible. It's called a singular matrix. And we kind of already know the name because invertible matrix is called non-singular. So it's a kind of a negation, double negation here. So invertible means non-singular, and singular means not invertible. Okay, it's just a name here. Okay, and as we said, intuitively a singular matrix is 0 somewhere. Okay, and we'll get a bit more intuition on this somewhere on the later part of the course. Okay, and from this example, we see a 0 here, make it singular. And also similarly, this matrix with a 0 here is a singular matrix. Okay. Okay, that's a singular matrix. It's just a definition, but also important to remember the name. So when we say singular, it means not invertible. And here we have a small theorem. So if multiplication of 2 matrices and you try to find its inverse, then it's multiplication of the inverse. But the important thing happen here is that you want to invert the order. So AB minus 1 equal to B minus 1 times A minus 1. Okay. And yeah, so here is a bit of proof. So we try have this AB minus 1 multiply on AB and have it back to identity. So this is B minus 1, A minus 1 multiply on AB. Then we can just use the associative rule to to click together things turns in the middle. So we first resolve this A minus 1 on A, and A minus 1 on times A. Then by property of this minus 1 become identity matrix. And we know identity matrix multiply everything is still the same thing, so we can get rid of this on this chain of multiplication. And we get this just b minus 1 on b, so this is back to identity matrix. And then we can check that this is also the right inverse, so ab on b, ab multiplied on b minus 1, a minus 1, then this b minus 1 become identity, then this a minus 1 become identity. Okay. And we can extend this rule to a chain of many matrices multiplying together and having minus 1, so we reverse order on everything and have minus 1 on everything. Okay. And you can easily check that. You have this similar proof. You have this chain multiplying a1 to ak, it will give you the identity matrix. Okay, so those are the properties in matrix inverse in the equation. If not, then yeah, and we go back to talking about algebraic rule for transpose. So we define transpose before as the matrix where you just flip its row and column. And there are some rules for transpose. So for example, if you transpose twice, so for row to column, you flip column back to rows, then it becomes the same matrix again. And if you transpose, you scalar multiplication and then transpose, you can take out the scalar multiplication. And similarly, you have addition and then transpose, then just transpose on each element. And I guess a bit of interesting one is this multiplication and transpose, then you become transpose and multiplication, but with reverse order, just like inverse. Okay, and yeah, and you can do we skip the proof, but if you want to do the proof, you can just do the elements calculation. So you calculate the ijth element of this AB transpose and write down all the summation with indices, and they will see that it matches this side. Okay, let's skip that. And I guess this can be done as a homework for writing proof. So maybe we can do this as a homework. Okay, let you get familiar with this thing. Okay, these notations. And anyway, let's see some example of this working out. So A and B are those two matrices. You can do multiplication, it becomes this matrix. And I guess this is also kind of a proof. So AB says this 3 two-element of AB is the third column multiplied by the third row multiplied by the second column of A and B. And now I think about AB transpose. So this 3 two-element correspond to these 2 3-element, and this 8 will be the the second row of B multiplied by the third row of A, and yeah, and then we know, second row of BT multiplied by the third column of AT, and we know this second row is equal to this second column, and this third column equal to this third row. Okay, so that's a bit of an intuitive proof of this transpose rule. But if you want to be fully clear, you can write down the element-wise proof. Okay, and that's an example. And here are some checklists for this section. We have matrix multiplication rules, and we define identity matrix. And I guess here we also define standard vector. I should write here. Standard vectors, and those are those EJ, because I like J. And then there are matrix inversion properties, and you have this A minus 1 times A equal to identity equal to A times A minus 1, and A minus 1 is unique for ABA, and also AB minus 1 equal to B minus 1 times A minus 1. And we have this named singular matrix, means the matrix that's not invertible. You cannot find the M-1. Then we have transpose rules, and for example, we also have AP transpose equal to B transpose A transpose. Okay. Any questions so far? It's still easy. Then we go to more part that's also easy, but a lot of notation. So now we talk about elementary matrices, but really this is just writing linear system equation in terms of matrix notation. So remember, we can already solve the matrix in section 1.2. We can already solve a linear system equation using this Gauss-Jordan elimination, and we get reduce the row echelon form, right? Remember, we can already solve the linear equation with elementary row operations and getting your matrix into reduced row echelon form, and you can solve a linear system equation. And now we just write everything in terms of matrix, and in particular we have those things, and we have in section 1.2 we have the elementary. Sorry, I'm spelling English wrong. I guess that's not spell elementary. We have the elementary row operations, and basically what we do is we write the row operations in terms of matrices. That's what we do in this section 1.5. So the elementary matrices are just corresponding to the elementary row operations. Okay, let's write down elementary once again. Elementary. Okay. And anyway, so let's run everything once again. So remember, we already said that we can use this matrix multiplication to write the linear system as AX equal to B. Okay. And now we multiply both sides by a non-singular n by n matrix. Then the system will be equivalent, and this is something we prove down here. So say we have AX equal to B, then we write down another equation in that MAX equal to MB, where B is a non-singular n by n matrix. There is the inverse of the matrix. Okay. And so if we want to say those two systems are equivalent, we need to prove two things. So we need to prove a solution to 1 is also a solution to 2. And so what's a solution to 1 means there is some x such that, so we already fixed A and B. So there is some x such that AX equal to B, then that x will satisfy MAX equal to MB. And that should be pretty intuitive, because A equal to this thing equal to this thing, then we multiply by some matrix that will also send us the thing multiplied by this matrix B. Okay, so solution on 1 equal to solution on 2 is pretty clear. And then we need to prove the other way. So solution to 2 is also a solution to 1. So some x vector is a solution to 2. And we also want to say it's a solution to 1. And here we will show, okay, so we should fix the notation. So there are some other book that has head as a notation of vector, but for our notation there should be no head, so let's pretend the head doesn't exist here. So some x vector is a solution to 2, we want it to be also a solution to 1. And then we need to make sure that multiplying this matrix M don't give us more solution basically. And then here we use the fact that M is a non-singular, so we multiply M minus 1 on both sides of the solution equation. So something as a solution to this is also a solution to this equation. Okay, because we are just multiplying a matrix on both sides. And then we use that M minus 1 is the inverse of M, then M minus 1 will cancel M minus 1 will cancel M here. So something as a solution to this is also a solution to this, where is it just Ax equal to B. So we see that x is also a solution to 1. Okay, and yeah, and so we see that if M is invertible, then solution to 1 is equal to solution set to 1 is equal to solution set to 2. Okay, and we can do this many times. So if you apply a sequence of non-singular matrices, E1 to E2, then so like this. So E1, E2 to EK on AX equal to E1, E2 to EK on B. Then solution to this thing will be same as solution to this AX equal to B. Okay, and yeah, and all the solution will be equivalent. They have the same solution set. And now we try to find, now go back to this elementary matrix. So we found some non-singular matrix that will make our A into some very nice form. Okay, and that's the elementary matrices, and the elementary matrices are just the matrices that are corresponding to our elementary row operation. Okay, and yeah, and what they do is they are the matrix that you do elementary row operation on the identity matrix I. Okay, is the definition. So if you do one elementary row operation on the identity matrix I, then it's an elementary matrix. And the first type is corresponding to the elementary row operation of interchanging rows. And so the identity matrix look like this, and then you interchange two rows of it. Then you interchange the first row and the second row. Then you will get this elementary matrix, this 0, 1, 1, and 1, 0, 0, and 0, 0, 1. And the nice thing about this is you see that you can use this elementary matrix to do elementary row operation. So we see that you multiply E1 on A, then you will actually interchange the two rows on A. Okay. And yeah, so we just do the multiplication, you see change those two rows. And then there's other thing you can do that is less clear. If you multiply it on the right, then we'll interchange the columns of your matrix A. But for now, this one is more important. You need to remember you do this interchange of elementary matrix on the right, interchange the rows here. So you will interchange these two rows. Okay, interchange here. And similarly, you have type 2. You multiply identity matrix, a row of identity matrix from a non-zero constant. So say you multiply the third row by 3, and you get this thing. And you see that you multiply this elementary matrix on matrix A, then the corresponding row gets multiplied. Okay, so we have these 3 here, and you multiply on this matrix, then the third row will get multiplied by a 3 here. And also similarly, if you multiply this on the right, then the third column will be multiplied. And finally, we have type 3. You add a multiple of a row to another row. So say you add 3 times of the third row to the first row. Okay. And you get this elementary matrix here. Okay. And yeah, and we see that we kind of skip the order. Okay. Sorry. And the ordering is be weird. Okay. And this thing will also give us. So if you multiply this on matrix, will give us also the corresponding row operation. Okay. And I guess will be together in this 1.5, and let's do this here. Okay. So if we have a more general form, we have adding m times of the ith row to the jth row, so we get this elementary matrix, and let's see. No, this is a different theorem. Sorry. Okay. And anyway, we didn't have example here, but if you multiply E3, you guys that's right here, and if you multiply E3 on some matrix A, then it will also equal to A with the so that's right, the row vector. So will be so remember A equal to A1, A2, and A3. And if you do the multiplication, you will be A1 plus 3A3 and A2 and A3. Okay, so that's what the elementary matrix will do. You multiply on the left, you will do the corresponding elementary row operation. So you see that we can do Gaussian elimination with by just multiplying the elementary matrix to turn A into the reduced row echelon form. Okay, and here is some note. So if you multiply A on, so this is a part that we can do elementary row operation. So if you just multiply those elementary matrices on the right of your matrix, then you can do the corresponding row operation, and that's how you can turn A into reduced row echelon form. And similarly, something that's also nice to know, but not so pivotal to us for now, is that you can multiply the matrix on the right, and you will do actually column operation with the matrix. Okay, and then we have a theorem that's talking about the inverse of the elementary matrix. Okay, and so if E is an elementary matrix, and then we you can always find the E minus 1, and E minus 1 is also an elementary matrix. Okay, and for example, you have an elementary matrix that's an interchange of two rows. Then itself will be the matrix itself will be its own inverse. Okay, and that's because you this matrix will do interchange of two rows, and if you interchange those two rows back, it will become the identity matrix. Okay, and type 2 matrix is multiplying by a scalar, and you can always find its inverse is I guess here, sorry, and its inverse also the same type. It will be just multiplying the inverse of the scalar. Okay, because the scalar is non-zero, you can always find its inverse. So it was alpha here, you just multiply by 1 over alpha. Okay, you can inverse this elementary row operation. And the third type is you add m times of a row to another row. And you can just add the minus m times of a row to another row, and this will cancel the elementary row operation. And you can also do matrix multiplication out to see that this matrix multiplied by this matrix give you the identity matrix. Okay, And yeah, let's go back a little bit to linear system. So we say matrix B is row equivalent to matrix A if you can do a whole bunch of elementary row operation to go from matrix A to matrix B. And to write down this as a matrix, you say you are multiplying a whole bunch of elementary matrices. Okay. And matrix B is row equivalent to A if you can do a number of row operations to go from B to A to B. This is something you can already know from section 1.2. Yeah. And then from analysis before, we see that two augmented matrices are row equivalent if only if they have the same solution set. Okay. And same solution set also means A is equal to B are equivalent system. We're just saying we're just talking about the same thing with different notation. We can say those two are equivalent system, or the linear system have the same solution set, etc. Okay, and then we now have more, yeah. And also now we have the third way to say this. We can also say these two augmented matrices are row equivalent. So just different names for the same phenomena. It's either row equivalent or equivalent system or equivalent solution set. Okay. Yeah. And now we derail a little bit to memorize yourself with a bit of logic. Okay, and yeah, let's go back to a little bit of logic. So so we have something implies something. So say Jack will eat a fruit, and it is it is ample. So let's say this statement is A and this statement is B, and we can have translate English into statements. So say Jack eat a fruit if it is ample, then this means the statement B here implies the statement A, because this statement implies the statement, and in terms of logic we write this as B imply A. Okay. So and this is called B is a sufficient condition for A. So basically we are just introducing notation. So you can write in English in this way. So statement A if statement B. Okay, so this statement A here and statement B here, and we can write in arrow notation. So B imply A, and also write in another English, B is a sufficient condition on A. And then the second thing is statement A if only if statement B. So Jack will eat the fruit only if it is ample. And this actually means that statement A implies statement B. And this means B is a necessary condition for statement A. Okay. Because only if B happen, A will happen, and this means A happen, B will also happen. And then there is this thing that we talked a little bit before, that is Jack will eat the fruit if only if it is ample. And this if only if we will abbreviate as IFF, and in terms of arrow notation we will have B double arrow with A, and this means A, B is necessary and a sufficient condition for A. So this happen, this will happen, and this happen, this will happen. So these two statements are equivalent. Okay, and yeah, and here a bit more basic logic. So if A implies B, then its equivalent statement is B didn't happen will imply A didn't happen. So not B will imply not A. This notation it means not. And also some equivalent statements. So if A is equivalent to B, then B is equivalent to A, and and not B is equivalent to not A, and not A is equivalent to not B. And here are some practice that I think we can skip over. And let's try to go to the first bit of complicated theorem. So it's a theorem that you should remember its result. Okay. So there are 3 equivalent conditions for being non-singular. Okay. And this theorem, I think itself is a bit of intuitive, but the derivation will use a whole bunch of logic derivation. Okay, so there are 3 conditions that says 3 different ways to say that A is a non-singular matrix. So first is saying that A is non-singular, means that A has an inverse. So other way to say this is A minus 1 exists. Okay, and then the other way to say this is that Ax equals 0 is only the trivial solution 0. So the only solution to Ax equal to 0 is 0. And then the third condition is that A is row equivalent to identity. And here we'll use kind of cycling proof, although it's not cyclic proof. Okay, we'll show that condition A implies condition B, then condition B implies condition C, and the condition C implies condition A, so that all 3 conditions will imply 2 others. Okay, and yeah, let's try to do this. So first, A is non-singular, implies that Ax equals 0, only have the trivial solution 0. Okay, and we use that A minus 1 exists, and then we try to derive something on this Ax equal to 0. So we know A minus 1 exists, and we try to have a solution set on Ax equal to 0, and okay, and the important part is the middle part. So from the Ax equal to 0, then we use A minus 1 exists. So we multiply A minus 1 on both sides. So A minus 1 on Ax and A minus 1 on 0. And A minus 1 on 0, because the vector is all 0, 0 vector is all 0, it will just give you a 0 vector back. And A minus 1 on Ax, then we use A minus 1, then it becomes identity on X, and it's just identity X. So we see that if A minus 1 exists, then from Ax equal to 0, we derive X must equal to 0 for every X. Okay, so whenever X satisfies Ax equal to 0, X must equal to 0. So this remember X is a vector, column vector, and 0 is a column vector. So this X column vector equal to 0 column vector. That means all the components of X must equal to 0. And yeah, so Ax equal to 0 only have the trivial solution. And then we use condition B to show that condition C. Okay. And so from condition B to show condition C, we start with Ax equal to 0, only have the trivial solution. Okay. And from here, we first use the elementary row operation, or multiplying with elementary matrix, and we reduce A to the reduced row echelon form. And let's say the reduced row echelon form equal to this Ux. We kind of had this notation before that, but we didn't say what it is. And but anyway, this U means the reduced row echelon form of A if you do Gaussian elimination on it. Okay? And yeah, so U is obtained by multiplying those elementary matrices on A. Okay? And well, we know because we know that Ux equals 0 and Ax equals 0 has the same solution set, because we multiply with elementary row operations, and so Ux equal to 0 also only have one solution. Okay, and then now we need to think a little harder. In the middle part, there is a bit fishy, but we think we analyze the reduced row echelon form UX. Okay. If we want the reduced row echelon form only have one solution, then there can be no free variable. Okay. Because if you have a free variable, then we know there are infinitely many solutions. Okay, and then we know U is a square matrix, and then you just try to place together a reduced row echelon form for a square matrix. Then we see that if there is no free variable, then the only matrix U can be is this diagonal on all ones. Because say you start with 1 here, and since there is no free variable, then the next one must be on next row, and the next one must be on the next column, and then there are same number of rows as the same as the number of columns, so all the diagonals must be ones, and then there must be zeros all over because you are in reduced row echelon form. Okay, and yeah, so we see that U must equal to identity. The reduced row echelon form must equal to identity, and but we know this U is equivalent to A, and so we know identity is equivalent to A. Okay, so we prove B to C. This is a quite complicated proof. Any question? And if not, then we go back to proof of C equivalent to A. Okay. And then if A is a row equivalent to identity, then we can find the inverse of A explicitly, because we know there is a sequence of elementary matrix E1 to EK such that I guess it's a bit funny. Anyway, A is row equivalent to identity, so you can do a whole bunch of row operation on identity to make A to make it turn the identity matrix back to A, and yeah, and the string of matrix multiplied by identity is the string of matrix, so A just equal to this string of elementary matrix. Okay, and we know this string of elementary. We know every elementary matrix is invertible, and and yeah, and so A inverse is inverse of this string of matrix, and it's just E minus 1 times E minus 2 times all the way to E1 minus 1, E2 minus 2, all the way to EK minus K, etc. And because we find this inverse, so A is non-singular. I guess we have easier way to do the proof here. If we do the other way of elementary row operation, so A is equivalent to identity, also means that we can have E1, E2, to EK on A equal to identity matrix. So we can do a whole bunch of row operation on A to get it to identity matrix, and then this thing is just A minus 1. So this is the faster proof. Okay, because if A something is a row equivalent to something, there is a string of elementary matrix. You can multiply on it and make it equal to identity. And yeah, then this matrix string of matrix multiplying together is A minus 1. Okay. So yeah, this finish our proof. We prove this arrow, and this arrow, and so all those three. Excuse me, all those three properties are equivalent, statements are equivalent. So and those three statements are A is non-singular, and A is equal to 0, only have the trivial solution, and A is row equivalent to identity matrix. Okay, any question? This is the most complicated theorem proof in this chapter, and yeah, for now it's kind of theorem out of nowhere, but later on we'll see that this theorem has more meaning on linear systems and linear spaces. Okay? It talks a lot about being non-singular. Okay, and last theorem 1.5.2, and and we have a corollary to that that statement. So 1.5.2 talk about being non-singular, a matrix being non-singular, and this has implication on linear systems. Okay, and we translate it in terms of linear system of this A is equal to B, and and we see that this 1.5.2 translate to that A is non-singular if only if A is equal to B has a unique solution. Yeah. And so this A is non-singular is like a statement A from the theorem we just proved, and A is equal to B has a unique solution. It's like the statement B of the previous statement. Okay, and there are two ways to prove, two directions we need to prove. So we have if only if. So we need to prove that this statement implies this statement. Okay. And yeah, so it's similar to previous proof. So from A to B, we have A is equal. If A is non-singular, then for A is equal to B, we have that A minus 1. We will multiply A minus 1 on both sides. Then we have that X equal to A minus 1 times B. And yeah, so X must be this unique vector that's just A minus 1 times B. Yeah. And for the other direction, and for the other direction, we have a more complicated proof. So suppose A is equal to B has a unique solution, then A must be non-singular. And here we do a contradiction proof. So we suppose A is singular, and we derive a contradiction, then that means A must be non-singular. Okay. So suppose A is singular, then then from the previous theorem, okay. So here we use 1.5.2. So if A is singular, then from so A is singular is the negation of A here. So negation, because all those three conditions are equivalent, so you have a negation of A, you also have a negation of B and a negation of C. Okay. So negation of A implies negation of C, negation of B, and negation of B says that A is equal to 0 has a non-zero solution. Okay. Remember, this is a homogeneous system, and you have more than one solution, and I guess it's not important about homogeneous system. But anyway, it has a non-zero solution, and the solution that's z not equal to 0. Okay. Solution z not equal to 0 such that az equal to 0. And now let's let y equal to x hat plus z, where x hat is this unique solution here. Okay, so suppose we have a unique solution x hat here. Okay. And because z is not 0, then x hat plus z is a different vector from x hat. So y not equal to x hat. Then ay equal to, so the interesting part is this line. And this this line will use similar logic a lot later on, and this line is also why we like a homogeneous system. So we now think about what's AY. So this matrix A multiplied on this vector Y is, well, Y is just X plus Z. Then by distributive rule, we have this equal to AX plus AZ. Then AX equal to B because AX hat equal to B because this is how it defined. And AZ equal to 0 because it's a solution to homogeneous equation. And B plus 0 is just B. So we see AY is also equal to B. Okay. And then we see that Y hat, Y don't equal to X hat is also a solution to AX equal to B. Okay. But then this contradicts with our assumption that AX equal to B has only one solution. And so we know that A is singular cannot happen. A must be non-singular. So if A is equal to B has a unique solution, A must be non-singular. Okay. And sorry for going over a little time. And so if you have any question, you can ask me after the class, and we'll stop here. So see you Wednesday.
请问写作业可以用在纸上写，然后再拍照变成 PDF 吗？
应该可以啊。
OK， 好。